Exceptions to the octet rule. There are many compounds whose Lewis dot structures do not follow the octet rule. Specifically, these are compounds for which at least one atom in the structure, besides hydrogen, cannot be made to have an octet of electrons around it. These exceptions fall into one of three categories. Ions or molecules with an odd number of electrons. Ions or molecules with less than an octet. Ions or molecules with more than 8 electrons around one atom, an expanded octet. Let's start with ions or molecules with an odd number of electrons. Species with an odd number of electrons are relatively rare and usually quite reactive. With an odd number of electrons, it is impossible to get every electron paired, and therefore it is impossible to fill the shell of every atom in the structure. At least one atom, usually only one, must be missing an electron. Let's look at the example of NO2, which has 17 valence electrons, 5 from the nitrogen atom and 6 each from the 2 oxygen atoms. There are 4 possible structures for NO2, 2 pairs of equivalent structures. 2 have the unpaired electron on the nitrogen atom. 2 have the unpaired electron on one of the oxygen atoms. According to formal charges, which pair is preferred? The top 2 structures have the oxygen with the single bond with a formal charge of -1, the nitrogen with a formal charge of +1, and the doubly bonded oxygen atom with a formal charge of 0. The bottom 2 structures have a formal charge of 0 for all 3 atoms. So the best structures have the oxygen atoms with a single electron. However, remember that since all of these are resonance structures, all probably will contribute some to the structure. The second type of exception is the one with fewer than 8 electrons on an atom. These structures are usually rather reactive since they are electron deficient. Consider BF3, which is a classic case. We can draw a structure that satisfies the octet rule by making a double bond between one of the fluorines and the boron. However, as the formal charges show, making a double bond to fill boron's octet would give the fluorine a positive formal charge. This certainly would not correspond to reality, since fluorine is the most electronegative element known, and so much more electronegative than boron that it is hard to imagine that the electrons would spend time around the boron rather than the fluorine. Therefore, while the structures that put a double bond between boron and fluorine may contribute some to the overall structure, they are much less important than the one that leaves boron with only 6 valence electrons. So instead of having a double bond and having fluorine be positively charged, the boron simply remains electron deficient. So the lesson is this: if filling the octet of the central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, don't fill the octet of the central atom. The third type is perhaps the most interesting of all, and that is the central atom has more than an octet. If we look at real compounds of phosphorus and chlorine, we find that there are 2 that exist, PCl3 and PCl5. We have already looked at PCl3. If we follow the general structure guidelines for drawing dot structures, then the phosphorus is connected to all 5 chlorine atoms. This is confirmed by studies into the actual structure of the compound. The only way that this can happen is if there are more than 8 electrons around the phosphorus atom. In this case, specifically 10. This happens fairly often. It is particularly a possibility with elements in the third, fourth, and fifth periods, and is never seen for elements in the second period. One suggestion is that these elements use their d orbitals to increase the bonding capability. Another idea is that there is just more room around the atoms that are lower down in the periodic table. We will look at that later. There are 2 problems to try for the problem sheet for this part of the lesson.